The photoelectric effect for potassium. The photoelectric work function of potassium is 2.3 electron volts. If light that has a wavelength of 190 nanometers falls on potassium, find part A the stopping potential in volts, part B the kinetic energy in electron volts of the most energetic electrons ejected, part C the speed of these electrons. So we're looking at photoelectrons here. Now, in part A, when we have a photon incident on the potassium electrode, there will be an energy deposited that is equal to Planck's constant times the frequency. And part of this energy will go to the work function, that is the energy required to release the electron or just release the electron from the surface. So HF minus phi will be the net amount of energy that will go into the kinetic energy, which is equal to the stopping potential energy E delta V S. So our work function is given as 2.3 electron volts. The wavelength is 190 nanometers. Therefore, the photon energy, HF, will be equal to hc over lambda. That will be 1240 electron volt nanometers divided by 190 nanometers. So remember that we have this shortcut for these calculations. Okay, so the stopping potential delta Vs will be equal to the photon energy HF minus the work function divided by the electron charge. So this will be 1240 divided by 190 minus 2.3 electron volts divided by the electron charge. Therefore, we obtain a stopping potential of 4.2 volts. Okay, now in part B, what is the maximum kinetic energy in electron volts? The maximum kinetic energy will be equal to E times delta Vs. So that will be just 4.2 electron volts. Now in part C, we want to know the speed of these photoelectrons. Well, we're assuming non-relativistic electron motion here, so the kinetic energy is 1/2 mass of the electron times maximum speed squared. So we will find that the maximum speed of the electrons will be 2k max over mass of the electrons square root. And if we plug in the numbers here, we have 2 times 4.2 electron volts, 4.2 times 1.6 10 to minus 19 joules, so electron volts converted to joules. Mass of the electron is 9.11 10 to minus 31 kilograms, that's the rest mass, square root. So this gives us a maximum speed of 1.2 times 10 to 6 meters per second. Okay, so in the photoelectric effect experiment, we're shining light 190 nanometers on a potassium electrode so that we will create photoelectrons. The the photoelectrons will be emitted provided that the photon energy is high enough to overcome the work function of the metal. So after this cutoff frequency, we have electrons that are basically emitted from the potassium electrode with a certain kinetic energy. And if we supply a potential that will be canceling this maximum kinetic energy of the electrons, they will be stopped. So this will be equal to E times the stopping potential. For the photon energy, HF, Hc over lambda, we have a shortcut. This is 1240 electron volt nanometers divided by lambda in nanometers. And the work function is 2.3 electron volts. So if we look at HF minus phi divided by the electron charge, this gives us the stopping potential in volts, 4.2 volts. What is the kinetic energy of the electrons for the most energetic photoelectrons? It will be E times the stopping potential, that's 4.2 electron volts. And if we assume non-relativistic electron motion here, which is the case, we have 1/2 mv squared is equal to the maximum kinetic energy, and the maximum kinetic energy is going to give us a maximum speed 1.2 × 10⁶ meters per second.